Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to all participants who have joined this webinar. So the topic today I'm going to deliver is vibration analysis from theory to industrial problems. Okay, as mentioned by the moderator, Dr. Nizamuddin, my name is Asma Putra. I'm from Faculty of Mechanical Engineering, IMC Technical Malaysia Melaka. My expertise is engineering vibration and acoustics. So it comprises of vibration is also noise. Yeah? So in the automotive industry, we call it noise and vibrations. In oil and gas industry, usually it's vibrations, something dealing with vibrations, and also noise. So professional technologies and also the holder of vibration analyst category 3 from Mobis Australia. So that enables me to join many projects, consultation project in several oil and gas and power plants in Malaysia, because to be able to be the consultant of for vibration especially, so they require the contractor to have vibration analyst category 3, so to recommend analysis, troubleshoot and everything. Okay, so I'm an academician actually. So what we do is usually as academicians. So maybe those of you who are outside academics wondering what academicians actually do. So we work every day, including weekends, because we love our jobs. Yeah. Because we love our jobs, that's why we work every day. So every day is Saturday, and Saturday we open. Especially in vacations, we also working, thinking about research and everything. Okay, so that's a joke around academicians. But the academicians can be very extensive, the roles. So this is the it's like a mapping of what a lecturer is doing along his career. So it can be divided into teaching, so that the many aspects, and also research. Also can be many aspects in research, and also in service, and also many roles we play for these three kinds of duty as academicians. But me myself would like to also divide it 3 roles of academicians as well, the same as the previous image. So teaching, research, and consultancy. So what we mean by teaching is the way we passing the knowledge, or we spread the knowledge, especially to students. And research is where we extend the knowledge. So the first one, teaching, is we spread the knowledge or passing the knowledge. Research, we extend the knowledge. And the third one is consultancy, we apply the knowledge. So this kind of 3 roles mostly I'm playing during my career as an academics. Okay, so this is teaching. We try to be an inspiration for the students to be the long life learner, for the students to be the long life learner. Even though they graduate from university, they will never stop learning. Research is how you extend the knowledge, so that we not expected to also stagnant in current knowledge. So we expect to grow in terms of knowledge. We do research, we publish papers and everything, and we teach, we train postgraduate students to be master, to graduate as an MSc, and then also PhD students as the important capital human for the country. Okay, so this is some part of the photos I'm doing as a consultant in oil and gas and also power plant industry, starting from effectively 2012 until now. Okay, so why we study vibrations? So let's begin on why we should study vibrations. So as the current technology, we usually we have high-speed engine. Yeah. We have high-speed engine now, and materials becomes lighter and lighter, lighter but strong, lighter but strong. But combinations of high-speed engine, high-power engine, and also light materials will always cause vibrations. So this one is still a challenging problem for many structural engineers. And if a structure is suffering vibrations for a very long time, so the most dangerous situation is fatigue, what we call fatigue. So this image is showing the micrographs, how the severe fatigue cracks occurring by time for the structure exposed to vibrations for certain quite amount of time. Okay, so this is a case study in Malaysia. So where we have a crack on a pipe, yeah, and then one of the module in the plant has to be shut down, and then the company will lose 2 million per day, 2 ringgit million per day. So this is a very serious problem, as we thought vibrations is maybe something which is very easy to deal with, but this is a very serious problem that engineers has to take care and monitor every day. The vibration level of especially structures in and very sensitive factory or plants. Okay, so this is the famous one where every lecturer will post this as a study case. In 1940, quite a long time ago. So this the massive structure of Tacoma Bridge can collapse only the extension from the wind. So it's not like a typhoon or heavy wind. It's just a usual wind flowing across the river. But actually, the natural frequency of the bridge coincide with that frequency of the vortex shading. So vortex shading is the phenomena of the fluid oscillation of the fluid due to interactions of the fluid with the structure. So that can cause the bridge to fail because of vibrations. And this is what happened in Rana Plaza in Bangladesh in 2013. So the building, which supposed to be for office, but they converted to garment. So Bangladesh is well known for the place where famous brand for fashion will be fabricated in Bangladesh. So they convert the building, which is supposed to be in the office, floating floor, and they put the machines for garment, generators and everything. So when they on the generators, they don't realize that this type of building will not support vibration input. So and the building collapsed and more than 1,000 people died. So it's a very sad incident at that time. And this one is Sayano-Sushenkayaka power station accident in Russia. So it happened in August 2009. So this is a turbine, massive turbine, rotating machine. But this the second one, the turbine number 2 failed because of something happened. Faults happen in the turbine, and there is a vibrations. So usually in rotating machines, the vibrations is indication of the machine will fail. So the engineers should be aware that if the vibrations level is increased, there's something wrong with the machine. So this one is maybe action is very late to be performed at that time. So this is what happened after the turbine blows up. So luckily only 75 people died compared to what happened in Dhaka, Bangladesh, more than 1,000. Okay, so vibrations can also excite noise. So noise is a very annoying phenomenon, and this is we can see what we call noise barrier along the railway. So if you want to see this kind of barrier, you can notice that at some part of the highway in KL, so where we have apartment nearby, and this is the road, and they put the barrier here. Okay, so from the train, the noise is not actually from the machines, from the machines of the train, but the most significant noise is from the frictions between the wheel and the rail. So because of that friction, the rail, this one is rail is vibrating. This rail is vibrating, so mainly low frequency, and that noise is very annoying. So because it's low frequency, the wavelength is long, so it can travel quite far. That noise can travel quite far because it's a low noise. Okay, so that's why they put this noise barrier. And also effect of vibration on health. So this is the guideline on how the tractor manufacturer they have to comply with the minimum amount of vibration level to prevent the user of the tractor, the driver of the tractor, to have back pain because of the too much vibrations from the tractor. So this is the guideline by United Kingdom. Control back pain risk from whole body vibrations. So this is how the vibration can affect the health directly to human. And also convert when we take the train, it's too much vibrations, or we have the car, it's too much vibrations. We're taking the bus, and the bus has too much vibrations. It reduces the comfort. It reduces the comfort of the passenger, and sometimes can affect the sickness, the motion sickness. It's not only motion sickness, but the sickness because of the vibration from the seat. Vibration from the seats, which really disturb the comfort of the passenger. Okay, so what causes the vibrations can be design, can also be manufacturing defect, assembly, installations, maintenance, and also operations. Okay. So a bit of background theory, because the title is vibration analysis from theory to industrial problems. So I started with a bit of theory. Okay, so usually if we want to model a machine vibrating like this one, so we as the scientists will try to first how to model this kind of motions with simple mathematics. Yeah, this is usually how the scientist is working, and then from that mathematics we will make analysis what parameter affecting the motions of the system. Okay, so usually we in vibrations we can model the system into three impedance component. Yeah, the first one is the mass. So we assume that this whole body of the machines is moving up and down. So this one can be considered rigid mass. So we put it the symbol here, rectangular, representing the rigid mass of the machines. And the second one is what caused the machine to oscillate, up and down in vertical is the spring. Is this spring, which is the flexible element. So the flexible element should have the stiffness constant. So that stiffness constant will determine how flexible is the spring or how stiff is the spring. If the value is high, it means the spring is very stiff. If the value is low, then the spring is a very flexible spring. Okay, so that the spring as well, we have damping. So in damping, we assume the damping to have like a physicus type of damping. Although in practice, we don't use this model, but this one for simplicity of the mathematics, we use the physicus damper. So physicus damper is the damper that we found in our motorcycle, So where we have the piston and also in the fluid inside the piston, inside the tube, physicus damper. So it's a very simple model because it's directly proportional. The force is directly proportional to the stiffness to the C, which is damping constant. Okay, so we assume what caused the vibrations of the machine is the internal force from the machine. So we assume it's to be F as a function of time, and we assume the force to be harmonic. Harmonic means it's like a sinus functions, and the amplitude is x. Let's say x is a function of time. Okay, from the equilibrium. So if we have the equilibrium line, so it will go up x, displacement x, and go down displacement x. Okay, so this is what we call mass spring and damper models in vibrations. Very simple model, and then we assume this one is a single degree of freedom system. Single degree means in this simple model, we assume these machines to only have the vertical motions. Because but in reality, it's not as simple as vertical vibrations, because the machines can go up vertically, can also rocking in horizontal, and also can also rocking axially if this is coupled with palm. Okay, but again, because we want to know, what is affecting the amplitude of vibration of this kind of machines from simple mathematics, and from there we can expand it to be a bit more difficult problem. So then we assume only single degree of freedom. Okay. So the effort is simplify the physics and the math. Okay. So then from here, we got the force. We got the force acting on the system. Yeah, so this one is, if you remember what we have been taught in since high school, yeah, m multiplied by the acceleration. So x double dot is the second derivative of f. So m multiplied by acceleration is the force from the mass, rigid mass, and c multiply the first derivations of displacement, which is velocity, and kx is the force from the spring. So this is equation of motion, and this is equals to F, internal force from the machines. So from here we can, because we assume the force is harmonic. Harmonic force means it's only simple sinusoidal function, and then we can represent the mathematics as the complex notation. We put it here. We substitute, okay, and then we end up with these beautiful equations. So you can see my YouTube how to derive these equations. So the students now, I refer it to my YouTube to see how the equation is derived. So we call it this one x over f is frequency response functions. So we want to know what is the amplitude of vibrations per unit force. What is the amplitude of vibration per unit force with respect to the frequency. Okay, so the frequency can be any frequency. So let's say the machine is running at 600 RPM, meaning 600 divided by 60 is 10 Hertz. So what excite the vibrations if the machine is rotating machines is if the machine, let's say, has N balance, so 10 Hertz. So can be 800 RPM, can be 1000 events, so it can be any frequency. Okay, so the equations here will be much more beautiful compared to the previous one. Okay, so if we take the previous one is complex number, so if we take the modulus, then we end up with this one. Okay, but we as the lecturer will not post this one for the student for the sake of just equations. So the students has to understand what is this equation is trying to inform us about the behavior of the system. This is much more important for especially for engineering students to understand, not taken blindly the equations as it is. So we have here the parameter, which is the stiffness of the system, and also the natural frequency, which is square root of k over m, and also the excitation frequency of the machines. Okay, so when we plot the graph, so we can understand much more here. We can understand more from the graph. We plot that equation, that previous equation, we plot it in the graph. We can use it Excel, very simple. So we end up with this graph. So this graph will tell us something as well. This graph will tell us something. So this one is the frequency of excitation. So let's say we can say simply this is the speed of the machine. If the speed of the machine is very low compared to the natural frequency, and what is the natural frequency? The natural frequency is the parameter of the system. So if you have the machine to have certain mass, and you have the spring to have certain value of stiffness, so the natural frequency of the system will be square root k over m, the natural frequency. So the natural frequency will be determined by the parameter of the system. What is the mass or the weight, and what is the stiffness, the mounting of the machines, that will determine the natural frequency. So the speed of the machine will determine the excitation frequency. So let's say the speed of the machine is here. So then the level of vibration is controlled by the stiffness. So 1 over k means if we want to reduce the level, if you want to reduce the level, we have to increase k. So this is what the graph is all about. It's telling us, is what the graph is telling us. So let's say if you want to reduce this level, means you have to reduce, you have to increase k. Mean you have to make the mounting stiff. yeah, or the flexibility, the motions of the machine to be restrained. If the speed of the machine is lower than the natural frequency of the machine. So that can be two different things. Natural frequency determines by the mass and stiffness of the mounting, yeah, or the flexibility of the structure. But what excites the vibration of the machine can be any frequency, yeah, which in the case of rotating machine is usually the speed of the machine. So the speed of the machine can also coincide with the natural frequency. So this is where the maximum vibration happen. Something that we should avoid, yeah, in engineering. We don't want the speed of the machine to be exactly the same with its natural frequency. If high frequency, then so in damping, in resonance, what control the level? This level is this damping loss factor, meaning we have to increase the damping. And then at high frequency, where the speed is much higher than the natural frequency, so we have to increase mass, yeah, to reduce the vibration. So this level is controlled by M. Yeah, so we have to increase M in order to reduce this one. Okay, so the moral of the story for force vibrations is, first we have to identify excitation frequency. Okay, and the second, we have to identify the natural frequency. So if you bring this concept into practice, if we face the problem where there is a high vibrations, the first thing we ask, okay, what excites that frequency? The second one, is it resonance? So we have to identify the natural frequency of the structure. So the excitation frequency, how can we know the excitation frequency? Usually from measurement. So we have to take measurement. We have to take the sensor, put it on the machines. We have the analyzer, and then we perform the measurement. And from there, we get the signals, and we know it is the frequency of excitation. Yeah. But for rotating machine, usually the speed of the machines. But if rotating machines is connected to pump, is connected to gear, gearbox, coupling, and so on. So the excitation frequency can be multiples of the speed of the machines. So natural frequency we can get from measurement, and also we can get from numerical modeling. So in vibration we have a finite element analysis. So we can perform finite element analysis to get the natural frequency of the system. Okay, and also in vibrations, the most important one is also signal processing. So signal processing is something has been done by the analyzer. So if we take the analyzer, we take the sensor, the analyzer will do the task for us. So the time domains, the vibration signal of time domains can be converted into frequency domain. So this one is time, this one is frequency. Okay. So fast Fourier transform, FFT. All right. So so let's see the project case. So from that theory, we move on the project case. So this one is what we did on what we call it sulfur recovery unit. So we have high vibrations at the oxygen intake pipe. So this oxygen intake pipe will supply oxygen into this combustion chamber, and then from the other side they mix with the gas from the from the platform, and then they burn it here, and then there's some process here, they release it here, some process, and they get the sulfur back. Yeah, from here they have the process to get the sulfur, which is previously it's mixed with another chemical, another gas. So after the burning process, they get the sulfur. Yeah. and then they can sell the sulfur. So what happened is that very high vibrations, on this intake pipe. Yeah, at some point they have to stop the operations because the screw, because of the vibration, the screw here almost loose, almost loose, which is a very dangerous situations. So when we measure, when we make measurement, so we can find a very high vibration at this single frequency, which is 93 hertz. Okay, so this one is what I mentioned before, from the signal, fast Fourier transform, signal processing, and then we get the frequency domain. So from here we can get, okay, the culprit of the vibrations is this frequency, 63 hertz. So we can see here the peak stand out, very high peak stand out, 63 hertz. Okay, so then we have to find where this 63 hertz come from. So this is usually what we did in what we do as a vibration analyst. So 63 hertz, what is it coming from? Is it from nearby machines, or from inside the chamber, or what is that? Okay, so then in order to kill all the possibilities, so because we want to make sure that our analysis will be correct, so we want to kill all the possibilities first. So we try to measure the air supply pump vibrations, and then we can see there is no vibrations of 63 hertz. Okay, and also we measure the SRU downstream or incinerator, so there is no vibrations frequency at 63 hertz, 63 hertz previously. So this one is not possible. Okay, so that one is not possible. So we kill first all the possibilities, and then we want to ensure whether the pipe is vibrating at resonance or not. Yeah? Because usually high vibrations, we suspect it vibrate at resonance. If it is resonance, then that will be dangerous situation, and we cannot let it go the vibrations to sustain at resonance. Otherwise, the structure will fail. Yeah? So we perform what we call bump test. So bump test is we have the hammer, and then we ask the client to off the operations for some time. So when the operation is off, we come into the site and we perform bump test. Yeah. So bump test is to bump the pipe, and then from there we got the response, and we will see whether the response has 63 hertz. So if you look at here, what we suspect, so in bump test, that high peak is most likely the natural frequency of the pipe. So it's not 63 hertz. It's not 63. Yeah? So 63 is somewhere here. So we relieve a little bit that the pipe is not in resonance. It's not vibrating in resonance. But something is forcing the pipe to vibrate. Although it's not resonance, but very high vibrations at 60 hertz. So 63 hertz is, if you want to imagine what kind of vibrations 63 hertz, it's you can imagine 1 second 63 oscillations. In 1 second, 63 oscillations. So we cannot see the vibration by eye. So if you come into the sites, you see the pipe, and then you will see the pipe is steady, no vibration at all, because that one is very high speed. But if you touch the pipe, then you can feel that it's vibrating. It's vibrating quite high. So you feel that your hand it's like there is an electricity coming into your hand. So very high, 63 hertz. So the one you cannot absorb by eye unless you have. If you want to know the level, you have to use the measurement device, sensor, and everything. Okay, so it's not in resonance. Okay, and then accidentally we after several visits, so the visit, the measurement on the site, it's not straight away one day we find the problem, no, because we have to go back and I think several times we going back into the site to make measurement, because the first time of the data we take it, yeah, we take it in the office, we look at the data and we try analysis. All right, so then if we think something and then we coming back and we take another data and we going back do some analysis, and then we cannot find the answer, and then we have other idea. Okay, so the last of the idea is why we we have the sensor of acoustic sensor, the noise, to measure the noise, and we use that acoustic microphone to measure the noise. So we put it somewhere roughly 1 meter facing the chamber, and then we measure the noise. So what we found when we measure the noise is this 63 hertz, 63 hertz and harmonics. So quite obvious. So means what? Means something, the source of 63 is something coming from the process inside the chamber, from this finding. So this finding that 38.5 is the noise from the incinerator, the previous one. So because we measure the noise, so all the noise will coming into our acoustic. So we cannot separate, but we can see the frequency. So this one we're not interested. But here we can see the noise, the noise inside from the chamber 63. Okay, and multiple. So we have the harmonics of 63. Okay, spacing nicely. So then the source of deprivation is something dealing with the process inside the chamber. Okay. So what we find is the pressure inside the combustion chamber, and this is related to thermoacoustic induced vibrations. So we have the nozzle that ignite the flame, and then it will burn the gas inside, and that kind of nozzle on and then flame and everything, it has a frequency. It has its own frequency. Now that frequency, that heat release fluctuation and pressure fluctuation, the combination of these two might be coincide with the acoustic mode shapes of the chamber. So acoustic mode shape of the chamber excite the acoustic mode shape, then the energy is feeding back, fed back to the oxygen gas. We cannot feel the vibrations of the combustion chamber because it's a very heavy, very large structure. But that kind of force is giving back to the oxygen structure, that oxygen pipe, so the oxygen pipe is vibrating very heavily. So it's considered low frequency dynamics, and the excitation inside the chamber, it's a bulk acoustic mode, means the whole thing of the pressure inside the chamber, uniformly exciting the oxygen. Okay, so this is one of the analysis for chamber vibrations. A bit more background theory. Okay, from that equation we can also derive the phase. So what does it mean by phase? Phase is it's how the force and the response will behave. Yeah? I mean, this one here is a zero phase. So zero phase means the force and the response will have the same phase. Mean if the response going down, if the force is going up, so the force will also going up. If the force is going down, so the force is also going down. So this is low frequency. So zero phase. 180 degree. So this is the opposite of the zero phase. So this one is if the force is go up, the response will go down. So it's opposite. 90 degree, it's somewhere in between. 90 degree. So it's like a motion of the piston, 90 degree. So this is very effective, very effective to excite the system. Okay, so we can also apply this one if we take 2 points. We take 2 points. Let's say if we take measurement point A and point B, and we end up with zero phase at that frequency, and then we can visualize the vibrations is moving together. The other side of the motor is moving together. 90 degree is something like this. Yeah. 180 degree is rocking motions. So when A is going up, B is going down. Yeah. B is going down, B is going up, A is going down. Yeah. So it's opposite directions. So we can apply the phase to from one point to another to see how the system behaves. From that informations of phase and amplitude. Okay, so this is the one that we did for this one system, motor gearbox conveyor system. So that motor has a speed of 1,500 RPM. Yeah, if you divide it by 60, is 25 hertz, around 25 hertz. So high vibration at gearbox. Yeah, so this gearbox is used to run the conveyor. So this conveyor, this is a coal. This is a plant, power plant site. So we conduct operating deflection shape to see what happened, the behavior of gearbox and also the motor. We call it operating deflection shape, ODS. So we record the amplitude and we record the phase, and to see how the motions of the system. Okay, so here we design the measurement points. Yeah. So we conduct up to 99 points. Up to 99 points. So we take measurements 99 points. Each point has 3 directions. So imagine how many measurement points we have. Okay, so 1 point, 3 direction, X, Y, and Z. And then we have total 99 points. So we measure from morning to afternoon. And around the coal also where the ashes is very, very high, so we have to put the mass every time. Okay, so this is the simulations of the vibrations. Okay. So this is the gearbox, and that one, the opposite one, is the motor. Okay, so if you look at closely, the gearbox is somewhat 185 degree from the motor and also from the gearbox. So something is not right with the coupling. Okay, so this one is from the other side. Yeah, so we can see here if this one is moving to the left, this one is moving to the right. So we suspect something which is something dealing with misalignment. So misalignment is the coupling between the motor and the gearbox. It's not straight, so something is not aligned. Okay, so then we also perform the analysis, frequency analysis, to make sure whether this one is really alignment. So 1500 RPM, 25 Hertz, we should expect 25 Hertz here, but this one is not 25 Hertz, but 50, 2 times 25 Hertz. So in vibration analysis, 2 times the frequency of 25 means something is dealing with misalignment, with the coupling. Okay. And also we have here MW kind of signal. MW kind of signal meaning we have the component first frequency and the second frequency. So this one is also indications of misalignment. Okay. So we took conclusion at the time is coupling misalignment. Okay. So this one is the examples of also the same one. Operating deflection shape for the piping. So this piping of the oil and gas company. So this one is important for the client to decide which one they have to put the brace in, where to put the locations of the brace to reduce the vibration of the pipe. Yeah. Sometimes the vibration is cannot be seen by eye, so it's difficult to take decisions where to put the bracer to hold the vibration of the pipe. Okay, so this one is another examples of our simulations. Yeah, so this one is all the measurement point. So you can see how many measurement points, up to 100, almost 150 points. So this is very extensive measurement we conduct just to animate the this kind of vibrations. But now new technology is coming now. So we have the camera. So the camera will capture the vibrations from quite a distance. So using frame by frame, the camera, the output of the camera, the video can simulate the vibration of the pipe. So this one is much more convenient technology. So we don't have to perform contact measurement. So we can have a bit more safe compared to where we have to come very close to the pipe, and we should put the H2S gas detector all the time. So if there is a leaking of H2S, we have to immediately leave the plant. Okay, so with the kind of new technology, we can have a bit more safe kind of measurement. Okay, so this one is motor vibration. So this one is we have the motor vibrate very high. So the motor runs at 2,965 RPM, around 49.4 Hertz. Okay, so this also we conduct the operating deflection shape, so we can see the motor is rocking from side to side. Yeah, it's rocking from side to side. So horizontal vibrations mostly. So when we make analysis of the signal, we find a very small amplitude at the speed of the motor, but we have 100 Hertz, very high vibration at 100 Hertz. So 100 Hertz is 2 times the line frequency, because in Malaysia for alternating current we use 50 Hertz. Okay, 50 Hertz, so 2 line frequency, 100 Hertz, very high. So that kind of line frequency is dealing something with instability of electricity inside the motor. So in vibrations, the analysis can be the possibility can be roto essence eccentricity, rotor eccentricity, and also loose static winding. So it can be that too. So we suggest the client to perform what we call current measurement. So from current measurement, they can know something is not right with the rotor or the winding inside the motor. So it's not really structured, because when we perform the operating deflection shape, the client wants to know whether there is a loose on the feet of the motor. Whether this one here we have structural looseness. We call it structural looseness. So if the screw here is not really tight, so it can cause vibrations as well. So they just want to know, want to confirm that one, whether that one is the problem. So the operating differential shape is not telling that's the problem, because if we have structural looseness, we're gonna have this one is from 0.17 or 0.18 will be out of phase. So the kind of motions is it's not opposite directions. So it's rock. This one is rocking like this one, but the base here is it's fixed. If we suspect there is a structural looseness, the base will somewhere from this side to that side will somewhere out of phase. Okay. All right. So that's all. I think because of the time, 1 hour. So I just put some of the case to share, just to present what is likely the theory we have in the class, and then what is the problem that we bring it into the applications and the knowledge. And it's good to have this story back into the class, so that the students can feel the application of learning the vibrations and to solve troubleshoot the problem when they got to work in the real life applications. Okay, thank you very much. I give it back to Dr. Nizam.
Okay, thank you, Dr. Azma. So it is a very informative presentation. Let me share. Okay. Right now, we are in the Q&A session. If there is any question from the floor, you can just unmute yourself and you can ask Dr. Azma. Okay. In the meantime, for those who can see the slide now, you can scan the QR code, or you can click the link inside the chat, and you can answer you can fill up the attendance and feedback form. So, Dr. Azma, there is one question inside the chat. Can you hear me?
Yeah.
Okay. The question is, may I know what sensor do you use to measure the vibration?
Yeah, in vibration we use what we call accelerometer. So from the name, it measures the acceleration, and then with the signal processing in the analyzer, we can have the velocity as well. So we can get the velocity. So accelerations, we can get the velocity. So the analyzer will perform the integration in the theory from the accelerations to get the velocity. We have to integrate. So we use accelerometer. We call it accelerometer.
All right. Thank you. Is there any more question? Dr. Rama, I have one question. Since you say to measure the vibration using the accelerometer, How do we know the sensor is good enough for our analysis, such as if you want to use the accelerometer from the spark fund only, or the one with cost maybe 1,000 ringgit for one sensor? How do we know? What's the
Yeah.
range?
So for the purpose of lab work, analysis we're doing in the labs, we usually use the sensor, very small accelerometer, which is very sensitive, can go up to high frequency, and quite expensive. But it can very sensitive to up to high frequency. Meaning, if you take that accelerometer to measure what any kind of vibrations from low frequency to high frequency, we can use that one. But in industry, the environment can be very harsh. Sometimes you want to measure the pipe which is very hot, so then you have to use the accelerometer which has heat resistance. So we use that kind of industrial accelerometer, which can, but it's not very expensive. Can be from 300 to 500 each, the accelerometer. But the sensitivity is not as high as the one that we have in the lab. The one we have in the lab the price can be up to 5,000 each. Yeah, very expensive. But for industrial can be very cheap. But mostly in practice, especially for rotating machine, the frequency the structural vibrations up to 2,000 is more than enough. Up to 3,000, more than enough. So we just use that accelerometer, and then that's it.
Okay. Another question. What are the advantages of using ODS over OMA from Dr. Azman experience?
Yeah, this one is Dr. Shah, my colleague. Okay. For ODS, OMA, we never use OMA, operating model analysis. But ODS is a very straightforward in industry practice, and the software is also very light. But yeah, operating model analysis with operating deflection shape, we not necessarily simulate the natural frequency of the structure, but it's only whatever drive whatever drive the vibrations of the structure. That's what we want. We simulate it. So operating model analysis it's very suitable on the structure which is vibrate at resonance. But for ODS, it's not necessarily in resonance. So any kind of force vibrations we can simulate with them.
All right.
Hope to answer. Okay. Currently, we have issue the end user of humming during running blower. Okay. 35 hertz. Need to run up to 40 hertz until humming noise disappear. Do we need to perform calculation or add dampener, etc.? Okay, so this one is a noise. Okay, so this one is dealing with noise. Blower. Humming during running blower on 35 hertz, need to run up to 40 hertz until yeah. Not sure about this one, but if something dealing with if 35 hertz causing noise, then there is something either so this is only my guess until we see this problem very closely. Maybe because 35 hertz is some frequency which excite the excite maybe the acoustic modes of the system. So either the outlets of the blower, something like that, coincide with 35 hertz. Because if we increase to 40 hertz, then the noise disappear. So this is something we dealing with that one. Yeah, that's the only one, the only thing I can answer. Yeah.
Okay. Thank you. And maybe this is the last question from Akmal Shafi. Do the gyroscope involve? Because I see the acceleration got direction.
No, we don't use the gyroscope. No. We usually there is one effective sensor, which is triaxial accelerometer, triaxial sensor, which one sensor can have 3 directions of measurement. But that one can be very expensive, and usually we use it in the lab. So we never brought it into in the sites. In the sites, we usually we just have three sensor. So we have 3 sensor with 3 cables connected to analyzer. So then if you want to measure, let's say the pipe, vertical and horizontal and axial, so we put 3 sensor at the time. Yeah, 3 sensor at the time, one at the top, one at the side, and then one is facing axial direction. So then we hit the measure button, then they measure. So we got 3 different data. So that's why when we make measurement, we consistency of recording the measurement point can be very important. So if we agree that okay, X direction is that way, Y direction is up, Z direction is going towards our body. So along the structure, we have to maintain that consistency. Because when we make analysis, we going back to office, we plot the data, so we know the directions of the vibration.